Hello Internet, my name is Quinn and this is Blondihacks. Working on my locomotive this week and we are going to make the boiler jacket, which is something that's going to keep our boiler toasty warm on those cold winter nights. Actually it's more like a clubbing jacket. Looks really cool, doesn't do all that much. You'll see what I mean. Allons-y. Remember those 2 videos ago when I was so optimistic and thought this is the last time the boiler will ever go on, and I insulated the steam manifold and put all the bolts in? Yeah, well, it's coming out, and definitely not for the last time. So I got to undo all of that work, and let's get ready to make this boiler jacket. It wraps around the barrel like so, and it leaves only the firebox exposed in the end. The cab covers most of the rear section of it. So I've got this big piece of brass for the job. It's very, very thin. This stuff's only 12 thousandths thick. McMaster calls it foil, which, I think that's a little hyperbolic, but it is thin. I'm going to mock this up in CAD because I only have enough material for one shot at this, and it's a very tricky and complex part. A paper template will ensure that I get it right, hopefully. This bar compass, if you're wondering, is a gift from a viewer many years ago, actually. I don't get a lot of chances to use it, but I do love it when I can. It was made in West Germany, which dates it to the 80s, the time of the best music and the worst economic ideas, and it's a beautiful set. I'm very lucky to have it and love a chance to use it. While I'm doing this, let me explain what a boiler jacket actually is. Of course, this is external combustion, steam that is, and so all heat is precious. The opposite of internal combustion, where heat is the sworn enemy of everything and you have to get rid of it. So we're always trying to insulate everything. So boilers are normally wrapped with what's called lagging in steam jargon, and then that lagging is held in place by the boiler jacket. Now this model does not have lagging on the boiler. And I know all the steam nerds are furiously flipping their tables while simultaneously engaging their caps lock keys to comment. Calm down. In the book, Kozo makes the case that at this scale, the lagging is so thin that it's really not doing very much anyway. The R value is minimal of that insulation. And if you want to keep the boiler's outer dimension at scale, then you would be forced to reduce the water volume of the boiler. And that is a very high price to pay. The water volume is the power reserve of the boiler. It dictates how quickly you can build steam for changing situations like climbing hills or getting started pulling a load and so on. So you really need to keep that water volume as high as possible, especially at 3.5-inch gauge. Now, I should know by now, history is littered with piles of bodies of messengers, but I wish you wouldn't shoot me for this one. He makes that case. I don't know enough about steam design to have an opinion on this. Go argue with him. Leave my comments alone. There is no lagging on this boiler, and this template fits great, so let's move on. At this point, you might think I would just trace the template onto the sheet metal and be done with it. That works fine in lower precision situations like making car body parts, that type of thing, but it's not going to be good enough here. I'm going to use the template as a rough guide in a few places, like rough cutting this material, and I'll use it for sanity checking as we go, but really it was more about sanity checking the dimensions on the drawing against my boiler to make sure I had built everything sufficiently accurately that the dimensions in the drawing are going to work for me. But transferring lines to sheet metal is a very sloppy process, and I don't want to trust it. As much as I can, I'm doing these cuts on the bandsaw because it leaves nice clean cuts and they're accurate. I sometimes am limited by the throat depth on this saw, so I do have a little section in the middle there that I couldn't reach, but that's okay. This stuff is so thin that I can actually, I think, score it and snap it with a good sharp utility knife. This is brass, and a few strokes with that knife, you can actually feel it cutting into the material. It's only 12 thousandths after all. On thicker material, I have other ways of doing this. I'll use a hacksaw or the Dremel or various other things, but you can also cut up the off-cut side to give yourself more clearance for the saw, but I don't want to do that here. I don't want to mangle the remaining material because it's useful for other things. But as you can see, this stuff's so thin that the old score and snap Yahtzees that off just fine. Now that was okay for the rough cutting, but when it comes time to final cut to dimension here, I don't want to use the bandsaw because it's hard to get a really nice, clean, perfectly straight cut on the bandsaw. So really the ideal tool for this is a shear, which I happen to have on my little sheet metal machine, and this material is very thin, so it should be within the capabilities of this machine. I don't use the shear a lot because it really can't handle very thick material, but 12 thou of brass should be no problem for it. Except, well, it just wasn't cutting it, so to speak. Yeah, look at that. That's just mangled that. This machine is love disappointment. When it works, it's amazing and incredible, and the rest of the time, it's disappointing. Luckily, though, sheet metal is pretty forgiving. We can flatten this out again and give it another try with some other method. The old score and snap was working pretty well, so I thought, well, maybe I can score this edge and give the shear a little bit of help. I'm not sure why it wasn't cutting, but maybe it's still a little bit too thick for this machine. I've learned not to overestimate this machine's capabilities. The shear in particular on it is very weak. And that seemed to do the trick. With a little help from that score line, that made a nice clean cut on that. Now for the longer side, same thing. I did a nice deep score on it with the knife, and this should have no trouble cutting through that. Should have no trouble cutting. Should just cut right through. Should have no trouble. Yeah. Once again, even with the help, it won't do it. This machine is maddening. Well, I decided to give up on it for this longer cut. I did a bunch more scoring and ended up simply flexing it as I did with that other cut, using a couple of rulers as straight edges to kind of keep the bending happening where I wanted it to, and this worked just fine. Again, you can get away with a lot with material this thin and being simply brass. The whole time I'm doing this, though, I'm thinking, that really should have worked. Like, why is that shear so inconsistent? It works perfectly sometimes and other times horribly. I mean, here, look at this. I'll do a couple little tests on that offcut, and like a champ, it'll bang through this stuff all day long. And that's when it hit me. In the middle, it works great. But on a longer cut, it starts the cut on the right edge, and it's the right edge that won't cut. So maybe that section of the blade is dull, or the blade might be a little bent. And then I remembered that, oh yeah, actually, this thing is adjustable. So I think the lower blade is attached to that platen, which is on slotted holes, and you can adjust it for clearance. And yeah, that end was pretty out of adjustment. Imagine that. A little tappy tapping later, and look at that. Cuts perfectly now all the way to that right edge. Now, however, we've got this large piece of material, and I need to verify the dimensions of it. And it's slightly over 12 inches, which means my largest normal caliper is too small. So you know what that means. It's time for Excalibur, 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 Excalibur. Of course, I store this in my surface plate, which is not very convenient, but it was prophesied in the codex, so gotta do it. Stupid codex. You see, because a surface plate is a stone. That's the joke. Look, you're the one who chose to watch this. Your hostess is someone whose arch nemesis is a royalty-free sound file. Quiet. So if you're subscribed, really, maybe you should think about what that says about you. Wait, come back, please. I like money. But I'm pleased to say the shear did an excellent job. Those dimensions are nailed. I'll just put that back, and let's move on to the next step, which is to basically duplicate the layout of the paper template. Again, I'm not just tracing the template. That's not going to be accurate enough. I want to do it separately with proper layout methods and just kind of sanity checking with the template as I go along. You know by now I like the surface plate for layout, but this piece is really too big and awkward for that, so I'm doing all bench layout. An engraved scale is really a killer tool for this. That allows you to set your dimension by feel in the notches on the scale whenever it's a standard dimension. However, if it's not a standard dimension, like if it's something in between, if it's not 30 millimeter or 3/4 or what have you, then I use this. It's a shop-made micrometer and caliper holder. Allows me to set any specific dimension that I want on the dividers and allow me to transfer dimensions and reflect them side to side and so on the part. Dividers are really critical for bench layout because most parts have a lot of symmetry in them, and they allow you to set dimensions more accurately and repeatably than just looking at a scale. So you set the dimensions with the divider, and then you connect the dots with the scale. And there we go. There's our finished layout. And everything was looking perfect according to the template, except for these two holes here, which are for the water inlets. They seemed to be off from the paper template. However, the paper template fits on the boiler, but the dimensions on the brass are accurate to the drawing. So which one is correct? The error was about 40 thousandths, which is not nothing. I checked the thickness of the template, which can affect dimensions like this on a round part, but it's actually just about the same as the brass, so no real difference there. In a situation like this, I look for a third source of truth to kind of triangulate, and I grabbed my seamstress tape and measured the distance between the water fittings and compared that to both the brass and paper templates to see which one seemed more accurate. And the paper was a little more accurate, but neither one seemed right on. I also sanity checked this method of sanity checking because the seamstress tape might be off or my approach might be wrong. So I measured some of the other fittings on the boiler and compared those to the brass, and those all lined up perfectly on the brass and the paper. So there's a discrepancy between the brass and paper on these last two fittings, and I can't say definitively if one is correct or neither is correct. It looks like maybe they both have some error, so what I decided to do was split the difference. I'm going to drill undersize between the two positions, and then I'll open it up with a file on final assembly. That way I don't risk either of them being wrong because I'm really not exactly sure which one is correct. So the rest of the little nooks and crannies get cut with the bandsaw and then finished up with the die filer and also a little bit of hand filing to get nice edges on things. I can't really use the shear for these types of cuts, of course. Luckily, this material is so thin that filing goes very, very quickly on it. Half dozen strokes, honestly, is all that's needed to achieve a corner radius, for example. For the big holes in the middle, I'll start with the smaller of the two because I have a step drill that will do that. Drilling holes in thin material is very challenging, actually, to do without destroying the material, and step drills are one great tool for that. So I'll line it up on my drill press with the pointy end of the edge finder, and then the float lock vise can clamp that down, and then I can bring in the step drill. I'm doing this on the drill press because it has a hole in the table, and the one cost you have to pay with step drills is you need a lot of room underneath the part, which in model engineering is frequently a deal breaker. So in this case, the hole in the table will do that. You can do it on the milling machine by putting a whole bunch of scrap material under the part, like sacrificial wood or something, but that's clunky and messy, so drill press will do the job. The reason step drills are good at this, if you're curious, is because of the cutter geometry. If you look closely under a magnifying glass at each step on a step drill, it has the same geometry as a boring bar on a boring head, for example, or on your lathe. That means the cutting forces are primarily down and a little bit sideways, and there's nothing creating lifting forces such as the flutes on a twist drill, which is what destroys thin parts like this. Step drills also make rounder holes. Twist drills actually make three-lobed holes all the time, but it's most noticeable on thin material because of their geometry. Step drills, again, they cut like a boring head, so they make rounder holes. I actually stopped one step before final dimension because I noticed that it was getting a little bit off from where my layout line is, so I'll leave it a little undersized and file as needed. And actually it does fit over the fitting already, but if it needs to be shifted a little bit relative to the other hole, then I've left myself some filing room. For the big hole though, it's too big for a step drill, so I thought I'll try the boring head. I might be able to plunge straight down in with the boring head. Depending on the grind on your boring bar, if you've got enough end clearance, like 10 degrees or more, and a small enough nose radius on thin material like this, you can actually do some amount of plunging with a boring bar. But not so here. This boring bar is not correctly ground to do this, and you can see it's just rubbing and it's never going to break through into the material. That means I'm going to have to start by clearing out the bulk of the material some other way so I can get the boring bar in there to start cutting. So I'm going to do that with chain drilling, which means using a twist drill on thin material, which I always try to avoid doing. Twist drills are very, very grabby on thin material, and they will yank it upwards and destroy it frequently. And again, I only have one shot with this part. There's a few things you can do to mitigate that distortion caused by the lifting forces. One is to get everything clamped down as well as you can. You can see I've got two of my sheet metal clamping bars that I've made all around the part, and I'm also using a block of wood to keep some downward pressure right next to the drill. The other thing is to use a smaller drill. The smaller the drill, the lower those lifting forces are. And the final thing is to feed very, very slowly, because the lifting happens as the drill breaks through to the far side of the material. That's when the spiral flutes grab it and rip it upwards. So if you make that breakthrough moment as gentle as possible, then you can eliminate the lifting. With that material out of there now, I can come in with the boring head, and with a boring bar, the cutting forces are all downward and a little bit to the side, so we don't have to worry about lifting. There's nothing that's going to be pulling up on the material, which is what makes the boring head good for this job. You wouldn't want to try to do this with a great big twist drill, for example. So a couple of passes with the boring head cleans up the chain drilling, and that is looking really good. I'll do a test fit now, and let's see if I need to do any filing or tweaking on things. Much to my shock, actually, that is a perfect fit on there. Look at that. Well, we are off to an excellent start on those 2 holes. There's a bunch of smaller holes for various fittings, and these all just have to be done with twist drills. There's no choice, so you can see me doing that here. Again, lots of clamping, very, very slow speed, and be patient. Don't let that drill break through suddenly on the far side. The next step is a weird one. Kozo has this kind of origami move that he does at the edges to create strong flanges for bolting the jacket along the bottom. So the way this is supposed to work is there's a middle section that folds under, and then the outer tabs get divided into thirds, folded under themselves, and then 1/3 of it folds back up to form a 90-degree flange, thus creating a double thickness flange all the way around that 90. And then the whole mess gets soldered together. And the book is not very clear on how to do this, and I studied it for a long time and practiced with the paper until I kind of figured out what Kozo was going for, and I think I did it right, but it seemed to work in the end anyways, you'll see. This is a tricky move though, and it's the part I was the most nervous about. I'm going to start by annealing the whole thing, because the softer this is, the easier this is all going to be. I will say I was a bit skeptical of this move also, because if it were me, I would probably just solder some pieces of bar stock to the bottom to create a thick flange that you can drill and tap some holes into. This kind of folded origami trick is not something I've seen before, but I'm going to give it a try because Kozo rarely lets me down, and he teaches me a lot in this book, so I like to do things his way and see if it's better than what I would have done. In the grainy darkness there, you can see me piling fire bricks on it to cool down. This material is so thin that just the act of heating it caused enough differential stress that it was warping, so I hoped piling some bricks on it would flatten it as it cooled. And I'm happy to say, once I exhumed it from that ziggurat, it was indeed nice and flat, so that worked. While that was cooling down, I put a chamfer on one of my sheet metal clamping bars, and that's going to help me with the folding steps, as you will see. I gotta say, these sheet metal clamping bars have been one of the best things I've made in the shop. They're literally just a piece of 2.5-inch steel angle hot rolled, and I cut one side short and machined various faces on it for clamping long, thin stuff. And I just keep finding new uses for them. They're so handy. Such as right here, I'm going to use the edge of my bench and these 2 bars, line it up with my scribe lines, and I'm going to fold the little center section down to 90 degrees, first of all. That's going to get this started. Then what I can do is flip it over, and using the now chamfered edge on the top bar, I can bend it over to 45 degrees, just with my thumb. It's so soft. And this allows it to get tipped over past the tipping point, if you like, which ensures the final bend will end up where I want it to. I'm also going to put some flux in here because all of these pastry layers of brass are going to get soldered in between. So what Kozo says to do is put flux in there, and then you can wick solder in there later between all of these layers once the folding is done. It's a very interesting technique, as I said, not something I've seen. Then while I'm here, I also do the outer 2 flanges, the first bend of several on these outer flanges. They get bent to 90 degrees, and then once again, flip it over, use the chamfered edge to get them to 45 degrees. Once again, filling the area with flux before sending it all the way home, thus creating the beginnings of our delicious millefeuille of solder and brass. Some steps of this process are going to leave things looking a little ugly, but not to worry, we can clean it up in the end. But also, all of this is going to be completely under the boiler when we're done, and none of it is going to be visible. So while I am trying to make it look nice, if it doesn't look great, that's actually okay. The main purpose of this is to have strength to be able to clamp tightly with bolts underneath the boiler. That's what this flange needs to do. So now I heat everything up and I flow some soft solder in there. Again, this came out a little messier than I'd hoped. I'm not using the greatest of techniques here, I confess, but as long as the solder is kind of flowing down into those layers, then it will do the job. And this seems to be working. I'm not going to claim I got 100% solder penetration, but it did seem to be working. The solder was running down in there. A smaller diameter of plumbing solder would have helped a lot. This coil I'm using is pretty thick, heavy stuff. It's for plumbing, so they're not intending to make pretty joints in 12 thou of brass material like this. Then I'm using a trick that I learned from my viewers, actually. You heat up the area again to liquefy the solder, and you wipe it down with a wet paper towel. And that gets rid of any excess solder blobs and smooths out the remaining solder, makes it look better anyway. It's a good trick. Then the final step, I take that whole soldered assembly and I bend that flange back down one more time to 90 degrees, thus forming the final flange that's going to have bolt holes in it and do the clamping of the jacket around the boiler barrel. This thing has been annealed like 50 times now, so this was not difficult. And those clamping bars really worked a treat. And look at that. That is really cool. You can see hopefully how there's a double layer there of brass bending all the way around now. And I gotta say, I am shocked at how strong that is. It really does feel as strong as a piece of bar stock soldered to the end of that. So I'm a believer in this technique. I'm converted because that is very impressively strong. All right, let's get this bent around the boiler now. It's, again, so annealed at this point that I can form it around the barrel by hand. And it was somewhere right around, wait for it, here's the moment, right, no, wait, I'm still working on it. Right there is where I remembered that, oh yeah, I forgot to open up the water fitting holes to their final size. So yeah, then I had to mark the areas where they're impacting the water fittings, and thus began a process of marking, test fitting, filing, test fitting, marking, filing, test fitting, marking, filing, and so on and so on. I am glad I did it this way, though. I think what I learned in the end is that one of the water fittings on one side is a little bit off, and that's why the paper and the brass seem to disagree. And also, paper is a little more forgiving than brass. It'll bend and fluff out in ways that brass won't, so that's also part of why the paper seemed to fit and the brass didn't. But in the end, I ended up with something that fits beautifully. Nobody was more surprised by this than me. Sheet metal work like this is absolutely not my forte. In fact, it's probably the thing I'm the worst at. So I was very pleased to have this work out. I am getting a lot better at sheet metal work through the course of this project, I will tell you. I've learned a lot. To drill out the bolt holes, I laid them out and center punched them, and then I drilled them out with a hand drill. I did try setting up on the mill, but there wasn't enough clearance around the curve for the big mill spindle, so this seemed to work fine. I'm running the drill very slowly here, again, to control that breakthrough moment so it doesn't rip upwards and distort the holes and damage the flanges. You could try drilling these from the other side to get clearance for the drill chuck. However, from the other side, you can't see where the bend radii are, and so you can't get the centers of the holes laid out properly. That's why I did it this way. Then I made up some little square nuts so that they'll remain captive on the flanges and I don't have to use a wrench to tighten everything together. You kind of need 3 hands to do this as it is, so if I also had to have a wrench on the far side here, it would be very difficult. A little clamp held things in place while I tightened these down, and while I was tightening things down, the clamp fell off, which is a good sign. That means the little clamping bolts are making everything tight and doing their job. I'm extremely pleased to say that all 8 of these holes lined up perfectly except one. There was one hole that needed a little bit of needle filing to line up, but very proud of myself again for getting that all to work out somehow. Getting the distance just right for a flange like this is actually quite difficult on boiler strapping and bands. I also ran bolts into the threaded holes for the handrails and the bell stud. Those all, of course, have to line up. I'm pleased to say everything did except the bell stud needed a little bit of ovaling out as well, so not too shabby considering my skill level and the difficulty of this part. Now we need to make some straps, however, and the straps go around this jacket and on the prototype actually hold everything in place. On the model, they are decorative. And I thought, well, I've tuned up this shear now, so this shear should be able to do this. Let's give this a try. Line up carefully on my scribe lines. Oh, like a boss. Look at that. That cut perfectly. Now that it's adjusted correctly. Beautiful. I really could not be happier with that. I'll just fill out my QC report here. I'm glad that worked because making perfect thin straps like that is actually quite difficult to do very many ways. Plan B was to use a fence on the bandsaw, but that wasn't going to do as good a job as the shear. Then we need the little L brackets that clamp everything together on the ends of the bands. So I did that with the old bread slice technique. You can see what I've done there. I've milled the L bracket shape into a piece of square bar. Then I drilled all the holes the correct distance apart for each bracket plus the kerf of the saw. And then I'm cutting them apart with a slitting saw. And as I always like to point out, a slitting saw is not a saw blade. It is a milling cutter, which means that it leaves perfect machined surfaces that are on dimension on either side of that kerf. If you did this with a bandsaw or a scroll saw or any other kind of saw blade, you are left with a rough surface on either side that has to be machined to be cleaned up, which means you have to leave extra material, and you have 2 machining cuts to make on each saw cut afterwards. A lot of work. Those brackets then get screwed and silver soldered to the ends of the straps, and then the screw heads are filed off, and we're left with very nice little thin straps with L brackets underneath them. To finish the boiler jacket, I decided to try powder coating it. You know I love powder coating. It's just such a beautiful, incredible process. Now, I've avoided powder coating things that touch the boiler because, of course, the boiler gets very hot. However, as we've learned recently in the thermal images that my viewers sent me, the boiler doesn't get as hot as I thought it did, and at least according to this thermal image, it's well below the temperature tolerance of this powder coat that I'm using, which flows at 450 degrees Fahrenheit. So it should be fine, I guess. I'm going to try it because if I can powder coat things, I always prefer to. It's way more durable, way easier, and looks a lot better when you're done. And well, if it doesn't work, if the powder coat melts, then it's not a huge deal to take this boiler jacket off, strip the powder coat off, and paint it with stove paint. But I really want this to work, so I'm going to try it. Powder coating is just such a joyous process. I really, really like it. It's so easy and requires very little equipment, and it's fast. You're not waiting days for enamel paint to cure, things like that. Like literally 15 minutes in the oven and then 15 minutes to cool down, and it's at full strength immediately. You can use it right away. It's just such a beautiful process. You can see how beautiful the result is. You can get all different glosses and colors. Oh, I love it. The other great thing about powder coat is that it is a flexible finish, so I can put this boiler jacket on here and I don't have to worry about bending it around and having anything crack or peel. I have my doubts that an enamel stove paint would stand up to this, quite frankly. And maybe the Brits out there are disappointed that everything is just black on this locomotive, but that's what we did on Canadian freight locomotives. It was very much form following function. Their only job was to shift tonnage and be cheap to maintain. And the way you do that is as it rolls off the factory line, you roll it through a fire hose of black paint. Now I am going to leave the boiler bands brass for now because it does look really nice and it's certainly not prototypical, but we'll see how I feel about it. I'm going to leave them brass for now, even though it does look a little toy-like. The other thing to know is that this brass will tarnish no matter what you do to it, no matter what kind of magic clear coat you think you can put on it, because it actually tarnishes from within, from the heat. Just being around a hot boiler causes it to tarnish. I've built enough boilers and tried every manner of coating and treatment on bands, and they all darken over time from the heat. There's not really anything you can do about it, but that's okay. Let's get it back on the chassis and see how it looks. Oh, look at that. Boy, it's really starting to look like a boat now. The cab's absence is certainly noticeable now because it kind of looks finished from the middle forward, but we've actually got a lot of work to do to work our way back towards the cab. But I'm really loving how that came out. Couldn't really be happier with it, honestly, and I learned a lot about sheet metal as always in the process. I hope you enjoyed watching me do it. Thank you so much for watching. Thanks to my patrons for making all this happen, and I will see you next time. Stupid codex.